Good morning, my BCS scholars. This is Mr. T coming from you from Mr. T's Science Lab. Okay, so I just want to say before we get started that I am immensely proud of all of my students. Um, you guys are doing an amazing job um, getting acclimated to this distance learning, to this remote learning. Though we are not physically together, I hope that you can feel my love through the videos. You guys are wonderful. You guys are amazing. And let's just keep on going until we see each other in the classroom again. Okay? So let's jump right in. So we spoke about last time energy, kinetic energy, potential energy. We touched on sound energy, chemical energy, but as we keep going in this unit, we will talk more about those things. But today, we're talking about sound energy and the effects it has, how it passes through matter. So let's get right into it, okay? See this guitar? This guitar um, is an acoustic guitar. It's not plugged up by any to any speaker or anything like that, and it is played by this wooden box, right? And these strings, and then this opening creates a sound, right? Creates a short or long sound. Once you pluck the string, that's what it's called. You will see it vibrate, but you will hear a sound, okay? Or you can feel it vibrate, and you'll hear a sound. Okay, sound energy. The blare of an alarm clock. Who hates that? I know I do. I'm sure you do too, Yusuf. The beep of a car horn. The quack of a duck. Isn't that funny? Right, Jade? Okay. And the rumbling of thunder during a storm. Are all sounds. Sound energy is the form of vibrations passing through matter. So it's passing through liquid, gas. So it's passing through matter, right? So so- sound bounces off solid, but it passes through liquid and gas. But you may feel the vibrations through solid matter. A vibration is a quick and back and forth movement. Sounds occur when objects vibrate. Sound travels through solids, liquids, and gas. Sound cannot travel through empty space where there is no matter. See, you can definitely, sound travels through solid. The waves will travel through. You can definitely feel the vibrations. Sound can sound cannot travel through empty space. Cannot travel through empty space. It's not light. Where there is no matter, matter is needed for sound. Matter is needed for sound. You cannot have sound out of nothing, okay? Cannot have sound out of nothingness. Because collisions between particles in the air gets heated and sound is produced. Pluck a guitar string and the string starts to vibrate. The vibrating strings collides with the particles in the air around it and passes energy to the air. The sound energy travels outward as sound waves. Okay? They sound makes waves. So when you feel the vibration, those are waves Those are waves coming through the matter, passing through that matter, okay? A sound wave is disturbance that moves sound energy through matter. When the waves reach your ears, the waves make your eardrum vibrate, okay? And we'll talk about an experiment I want you guys to do. You can do a couple of them in a video, but I'm going to talk about that when I get to the lesson and what you guys have to do for your independent work. You hear the sound made by the guitar string, okay? So I would underline words that tell what sound is. So you could underline sound is what? Is energy. Sound is energy. Vibrations. That sound is definitely vibrations. Sound is also it travels outward. Sound wave is a disturbance that moves sound energy through matter when the waves reach your ears. Okay, sound is a couple of things, right? It's not just one thing, right? So I underlined 3 things. Tell me, in your video, how many other things could sound be? Okay? How sound travels. As sound waves move through matter, they set particles into motion. The moving particles, remember we talked about the particles in the air, the moving particles form a pattern. Areas with groups of particles that are bunched together alternate with areas of particles that are further apart. So it's an alternating wave, right? And it's the moving of particles form a pattern. Areas that groups particles together. Remember, we said the particles have to collide. Those particles have to come together. And then sound is produced that are bunched together. See, when you play a drum, and this is a snare drum, it has a band of beads at the bottom that when you pop it or tap it, it vibrates. The area where particles bunch together are called compressions. Sound waves travel a different speed through matter. Sound waves travel quickly through most solids and liquids. Waves, those sound waves, not? So remember, sound has vibrations. It has waves that go through. You can feel the vibrations through solid. So this jar is solid, right? I could probably hear the water if I put it to my ear, right? The liquid shaking around in it. It's trapped. You see? Can you hear it? Right? It's traveling through the glass and through this tin container, this metal lid, and it's traveling through. So sound waves travel at different speeds. Sound waves travel quickly through most solids and liquids. Sound waves tend to travel more slowly in gas. So it travels more slowly through gas. So like thunder, we hear it really, really loud, but it travels slowly through. So always keep that in mind. So remember we talked about compressions, right? So the compressions are grouped together. alternating with other sound waves that are farther apart. So, circle the compressions images in this picture. Okay, so I would circle, what would I circle? This. Remember they said it has to be grouped together, those bunches of particles bunching together. Okay? So that's 1, 2, 3, 4. 4 compressions. And most beats have 4 beats. Most ranges have a 4 count or an 8 count. So when you talking music or drums, it's either you're gonna start on a 4 count and then or like in dance, 8 count. So she alternates. Sometimes when she's singing, alternates between a 4 count or 8 count. Mostly it's an 8 count. But in music, most times we operate in 4 counts. Or 8 count would be an octave. Okay, read a graph. This graph shows the speed of sound through some common materials. Use the graph to answer the following questions. Approximate speed. Okay. Approximate speed. Speed meters per second. So this is speed meters per second. And this is approximate speed. These are the approximate speeds. These are seconds. These are the approximate speeds. This is the name of the graph, the approximate speed. Speed meters per second. And this is the type of medium. So this is the materials they went through. Air at 0 Celsius, right? Remember, sound cannot pass through nothing. It cannot pass through empty space. Fresh water at 25 Celsius. Brick. 4. And the second would be, the meters per second would be around 1,500. 1,500. It would be around 1,500 would be the fresh water as it passed the speed meters per second. The brick would be at 4,000 meters per second. Okay? 4,000 meters per second. Steel, 5,000 is a little above the 5,000 mark, about 5,001 meters per second. Steel. So air, 0 Celsius and 0 meters per second. Fresh water. Ever try to speak underwater or blue bubbles underwater and you see those bubbles coming out and those waves it does make a sound. And you can hear the waves. If you're ever at the beach or wave pool, you could jump in and you hear the sounds and it creates waves. So it is at 1,500 meters per second, and it is at 25 degrees Celsius. Brick, about 4,001 meters per second that, sound is moving through. Steel, about 5,000 meters per second, okay? These are the types of mediums, and the questions are in your lesson. Frequency and wavelength. Waves can travel in different ways. They can carry different types and amounts of energy, but all waves have a certain properties. Frequency and wavelength are 2 of these properties. The frequency of a wave is the number of waves that pass a point in a certain amount of time. Frequency is often described as number of complete cycles and waves makes in 1 second. A cycle in one vibration. Wavelength is distance between a point of one wave and a similar point on the next wave. One way scientists study sound is by using Oscilloscopes. An oscilloscope is a device that takes sound waves and display the shape of the waves on a screen. Look at the oscilloscope screen below. The signals are displayed on screen in the form of a wave. Compressions in a sound wave show up on screen as crest or high point on the wave. The space between compressions show up as troughs or low points on the wave. Notice how the pattern resembles ripples in water. Waves like this one can be made in water by tapping the surface of the water. The ripples are the crest and troughs are the waves. So, see the wave. Low point, low point. So these ripples are the crest. These are the troughs. They're the low points of the waves. Wavelength can be measured between two crests or between two troughs. So it can be measured between these two, the crest, or it could be measured between the troughs. So if you measure between the crest, it would be about 100 meters per second. And if you measure through the trough, it would be about 0 meters per second. If this screen represented 1 second, this wave's frequency would be 2 cycles per second. So, the cycles. Oh, 1 cycle. So it'd be 1, 2. Okay, in our next lesson, we will be learning about pitch, and I have an exciting experiment for you. In that lesson, we are going to create more videos of you doing the experiment, and I am going to show my face on screen and do it as an example for you. So, with the lesson, you are going to make a copy of this, and you are going to save the copy. You're going to make a copy of this, you're going to save the copy, and you're going to work from the copy, okay? Does the sound explain how might one use sound if they can't hear? If someone cannot hear, how would they know that something is, that sound is happening around them? How would they know? Would they detect if something is happening or things are moving? What is the main idea of the lesson? So what is the main idea of this sound energy lesson? Does sound travel faster in air or in fresh water? To answer question 4, look at the picture below. See this picture below? About how many meters per second faster is the speed of sound in steel than in brick? Which has a higher frequency, a wave that makes 6 cycles per second or one that makes 10 cycles per second? Hey, make a video of sound energy. Can you feel the vibrations? Example, someone talking in your ear, not loud. I don't want anyone to have hearing problems later. Put your finger or hand over a speaker that is on and let us know if you feel the vibrations. Put your ear to the wall and see if you can feel the vibrations or someone walking or talking in the next room. I look forward to seeing your videos. So, these are all your questions. Again, you are going to make a copy of sound off 1, 2. Now, as you can hear, you hear that door, that's a sound. You heard footsteps, maybe, that's a sound. So those energy waves are the reason why I could hear it. And my eardrum did vibrate. I may have not felt the vibrations because it wasn't close enough to my ear, but do you hear all the sounds sometimes in the background? So listen, sometimes close your eyes and see how much sound how many things you can actually hear. Okay? So let's close our eyes right now. Yes, Aiden, you gotta close your eyes. Come on, Schneider. Close your eyes and listen. Don't tell anybody to be quiet. Don't say anything. Just close your eyes and listen to how much you can actually hear. Okay? So if I couldn't hear, I probably would feel something. What would I feel? Thank you, guys. So this lesson, remember, make a copy of this. Keep calm and keep using your school stomachs from Monday through Friday. Okay, guys? All right, I'm signing off, Mr. T. Keep calm and sail on.